Hi, this is Mr. Evans. Welcome to Room 310 Biology and our first video lecture of the school year. I'm going to be going over the scientific method and the nature of science. I know you've heard this since elementary school, you heard it in middle school, and guess what? This won't be the last time you hear it. You'll be talking about it in college as well. We use the scientific method to try to understand our world. In my classroom, we might mention some philosophic viewpoints, but philosophy is basically trying to think about questions which don't have a clear answer at all, and most of which cannot be experimented upon. Religious viewpoints are very, very, very important. But once again, we can't do a scientific experiment to verify something of a religious nature. So we're going to be concentrating on a scientific viewpoint and trying to understand our world and nature through science. We're going to take you back in history just a little bit. This is a piece of Egyptian papyrus which has been preserved. And this document is very interesting because though it's centuries old, it was written for doctors, and it was a treatise or a suggestion of how they should carry out their practice. When a sick person appeared to an ancient Egyptian doctor, they were supposed to observe the patient and take note of their condition. From that, they could set upon making a diagnosis, figuring out what's wrong with them, and then obviously you'd want to come up with a treatment. Give the treatment time to run its course, and it's either effective or we might need to go back and make a new diagnosis and then come up with a new treatment. I think you can see some parallels with what we consider the scientific method today. We'd also like to consider one of the most influential people in history, and that being Aristotle. Aristotle was a tremendous, tremendous thinker, very brilliant guy. He himself was the instructor or the teacher of Alexander the Great, and Aristotle was the student of Plato in ancient Greece. And this is Plato right here. You might notice in this very cool painting, Plato is gesturing upwards towards the heavens. That's where he's seeking his explanations. Aristotle, on the other hand, has his hand pointed down to the ground like he's saying, hold up a second, we can figure out things down here on Earth. Aristotle was, very, very, very influential, and one of the problems with being so doggone smart as he was held in very high esteem. No one really challenged him. He didn't really truly do experiments. For instance, he believed that heavy objects and light objects would both hit the ground at exactly the same time, which we know is not true because he never really did an experiment to carry it out. He did a lot of thought experiments in his head. He collected a lot of qualitative information describing things, but he did not use numbers and units as far as quantitative work. And that's probably limitations. He had no measuring devices. He had a sense of what's hot, what's cold, what's cool, but he had no temperature or thermometer with which to take a temperature. So that is kind of limiting. But he was very influential. Up through the Renaissance, people accepted his scientific ideas, and it wasn't really till Isaac Newton came along that some of his ideas started to be shelved and put aside as just what they were, fanciful ideas at the time. This gentleman, a Persian, great Muslim scientist, Abu Ali Hassan, was the first to really develop the scientific method. He really began to work it up more or less into its present form. He was primarily interested in physics. He did a great deal of experimentation on light and the behavior of light, which we might refer to as optics. But he really gets a lot of credit for developing, along with several other Persian scientists, a more modern view of the scientific method. We would, of course, be very, very remiss if we skipped over an Italian gentleman by the name of Galileo. Galileo, famous, of course, for supposedly dropping heavy objects off the Leaning Tower of Pisa, and he may well have done that. Once again, remember, he was a little bit limited in the lack of scientific devices for measurement. So it is well known that he built ramps and rolled either a heavy object or a smaller object down, and it was much easier to time an object moving down a ramp rather than just dropping a heavy object straight down, which was much more difficult to do. Galileo really improved the scientific method, gave us the heliocentric view of the universe, in which the Earth is going around the sun rather than vice versa, but this got him in a lot of trouble with religious folks. He did spend the later years of his life under house arrest for sort of going against the Roman Inquisition. Scientific methods continued throughout history with many, many influential people, and I'm just going to point out a couple here. Perhaps my all-time favorite scientist, the amazing Sir Isaac Newton, who in the course of just 1 year gave us the laws of motion, did a great deal of understanding of gravity, of light, and just invented calculus kind of in his spare time. Charles Darwin, probably one of my favorite biologists with his theory of evolution, but unknown to a lot of people, he did a great deal of experimenting. It wasn't just all a fanciful idea. He did a lot of research and many, many, many experiments. It's not just a man's game. Marie Curie, 2 Nobel Prizes to her credit, and a great deal of work in radioactivity. And then you can even get up to these guys, your Mythbusters. Well, are they scientists? Are they using the scientific method? I think we'd probably make the argument that they are following the scientific method, just in a little bit more entertaining fashion. So for my basic steps, and I don't have the only scientific method, I'm just giving you my take on it. Observation, we're using our senses. We look around the world, and if we're an interesting person and we're curious about things, we're probably going to develop a question. That's simply all we are. I saw something, I wondered why that was, I formulated a question. Our hypothesis. A hypothesis is not an educated guess. Try to get that definition out of your head. It's a little bit more to a hypothesis than that. It should be that if-then statement. If I do this, then I find that this will result. This hypothesis can never be completely correct, and it's okay if it's wrong. You're still learning something. If your hypothesis is incorrect, that's okay. But let's try and stick to using that if-then language. It'll make things a little bit more standardized for all of us. We're going to start moving on to a little bit of experimentation. We're always going to try to conduct a controlled experiment. And in that, we're going to have our IV, our independent variable. Variable being something that you change. It's an independent variable. Well, who's changing it? I am. I'm manipulating it. I am changing it. It is the one single thing in your experiment that ought to be changing. We have our dependent variable. The dependent variable responds to the independent variable. I like to think of it as the one we measure for a result. So if I do this, then this will happen. My if statement is my independent variable, and my dependent variable is the then statement. So is that all? Really, there isn't. There's a few other things that we need to consider. We're going to have some controlled variables, things that we are keeping the same. Might also refer to some of these as constants. If you don't have constants, you'll never be completely sure if the independent variable is causing the change in your dependent variable. So there's many things that we're going to have to keep the same, and we'll be looking at some examples of some of these in class. We also like to have a control group that we use for comparison. So if I think about my control group, maybe I'm doing a real simple experiment to see whether vitamin C prevents colds, prevents people from catching colds. A very famous scientist once hypothesized that. I'm going to need a control group, which is not going to be receiving an additional dose of vitamin C. My independent variable is the vitamin C, and I've got an experimental group that will be receiving those additional doses. But I still need that control group for the comparison. Was it the vitamin C that really made the difference, or was it something else? Data collection. Scientists are always trying to collect data fairly. We collect data in tables. And you will be making many tables this year, but we collect our data in a table, but we always display it on a graph. And you'll be getting a lot of graphing practice throughout your school career. Just remember, your x-axis is always going to be your independent variable, and your y-axis is always going to be the dependent. We'll talk a little bit more about labeling and axes and that sort of things, but these are the two really key ones. And it sounds silly, but I learned it a long time ago. Independent is a longer word than dependent. The word's tired. It has to lay down on the x-axis. Silly, but you might remember it that way. Our conclusion. Well, after all is said and done, we need to go through and we need to accept or reject our hypothesis. Remember, it's not wrong. We simply accept it or reject it. If we reject it, our hypothesis did not match, our results did not match what we thought was going to happen. We still learn something, so that's still beneficial to us. But there is our conclusion. Accept or reject. You look back at your question, was I right or was I wrong? Then we're going to need to publish. Science works by people writing things down and putting them out there for all the world to see. And in the world of the big scientists, people publish in what are called peer-reviewed journals. I've got the two biggies listed here, Nature and Science, but there are many others, some very specific, very tight-knit little groups, but these are the two really big ones. Many scientists are going to read your work. They're going to be writing in criticisms. They're going to be writing in rebuttals. Hey, you didn't think of this. And then the original scientist is going to write a rebuttal to that one. And they'll argue in print sometimes for months. But scientists want to be able to duplicate results. They want to be able to see that this is consistent, it's accurate. So people are going to spend some time rehashing things, and they're going to be doing some argument in print. You need a pretty thick skin, I think, at this point, because everyone's going to want to retest and make sure that those results are happening again and again. That's it for this show. We'll be doing quite a few experiments in class this coming year, and I look forward to using the scientific method accurately.